Okay, let's take a look at the first type of energy, gravitational or potential energy. Okay, so work is equal to force times distance, right? So here I'm going to have a force and I'm going to lift my object upward a distance h. So in order to do that, I have to lift, according to the second law here, I'm going to have to lift with a force of mg, and my distance is going to be h. So my work will be F times d, or mgh. Or probably a little more accurately, I should say that my mass times my gravity times my change in height. Because I assumed that this was a height of 0 here, and then I moved to h, but it doesn't have to be. I could have started at 10 meters and gone up to 20 meters, and I would have the same work done on the object. The same reason that I said that energy was highly dependent on the reference frame. So we should probably report it like this. Kinetic energy is energy of motion. And I'm going to show you this crazy derivation that you don't need to know, but I promised you I would do it early in the year, and so I want to follow through on that promise. Let's say I take a nice easy kinematics equation and say that my distance is equal to half of my initial and my final speeds added together. So this is really my average speed times my time. I don't want time in my equation, so I'm going to find acceleration is equal to my change in speed over time. And I'm going to rearrange and say that time is change in speed over acceleration, and I'm going to plug in up here. So I get that distance is equal to 1/2 of my speeds added together times my speed subtracted over a. And I'm going to rearrange, do a whole bunch of math here and get 1/2a, so I'll pull my a over here, times this mess. Well, this mess is nice and easy. It's actually gives me a difference of 2 squares. So my distance is equal to 1/2a times vf squared minus vi squared. And if I rearrange this equation, I've actually derived an equation that I told you I would derive later in the year. Vf squared equals vi squared plus 2ax. Now, the reason I waited to derive this is because it actually ties into energy. So if I keep going here, I'm going to bring my a to the other side. I've got AD equals 1/2 Vf squared minus Vi squared, and I'm going to multiply both sides by m. Well, m times a is a force, and d is a distance, so the left side of my equation here is work. And here, if I multiply this out, I get 1/2 Vf squared minus 1/2 Vi squared. Well, I'm going to define this term of 1/2 speed squared as a kinetic energy term. And therefore, my work is equal to the difference in my kinetic energies. So I need you to hold on to this equation of work being equal to 1/2 mv squared. Let's look at a weird example here. Let's say I take a box and I'm going to, this 10 kilogram box, and I'm going to lift it up 2 meters. So first thing I'm going to do is I'm going to define my energy as being 0 joules. I could have said that actually I have lots of joules, because who knows how much distance there is down here. But I'm going to say that in my reference frame, this thing starts with no energy. When I lift it up 2 meters, I'm going to have to use a force of mg, and I'm going to lift it a height of h. So my mass times gravity times my 2 meters, it gives me an object that now has 196 joules of energy. Now I'm going to slide that box over to the right, keeping the height exactly the same. How much work did I do? None. Because in order to move this box, I had a distance to the right, but I had to maintain an upward force. And since the force and the distance are at right angles to each other, I don't do any work. So my object still has 196 joules of energy. And you're going to say, well, what, Sterman, wait a minute. You moved it over here. Doesn't it have a kinetic energy? And I'm going to say, well, I stopped here. And although I was moving it, I stopped again. And so I don't have any kinetic energy when I actually take a look right here. Now I'm going to lower this block down to the ground again. So I'm going to drop it 2 meters. So I'm still going to need to support the object with a force of mg, but this time I'm going to lower it 2 meters. So I'm going to put in a negative 196 joules. And we're going to talk a little more about this negative sign soon, but for now you can just say, well, look, it was downward 2 meters, or another way to look at it is my force was upward and my distance was downward. And so I'm going to get a negative answer because this angle between them is 180 degrees. And if I take a cosine of 180 degrees, I get -1. So if I had 196 joules and then I gave that 196 joules away, my object is once again back to a 0 joule energy. And when I move over, I do no more work. So I went in a complete circle here and I returned with exactly the same energy. We're going to talk more about that too, because that is a property that says energy is conserved. All right, but that's a topic for another video. For now, I want to move on and talk about power. Power is the rate at which we do work. And power is going to be equal to our work over our time, because all rates are something divided by time. This equation is on your equation sheet, if I remember correctly. We measure work in joules, time in seconds. So you could say that power is measured in a joule per second, sorry. But we generally refer to that as a watt, after James Watt, who also did a lot of work with work and energy and power. The last concept for this video is efficiency. There are going to be times when we pump work into an object that kind of gets lost, either through friction or maybe it gets rid of it as heat. And so the total work that we get out is going to be different than the work that we put in. And efficiency is a ratio. It's equal to the work that we get out divided by the work that we put in. So we're going to start off with procedures that are 100% efficient, like the one up here. Any work I put in, I got out, so I had 100% efficiency. But that won't always be true in real life. Another way that we could do this is to look at the power. How much power did I put in and how much power did I get out? Because the time's going to be the same. So if we did work over time, if the times are the same, they're going to cancel. Efficiency, if you look, this would be a joule and this would be a joule, so there are no units for efficiency.